In this video, we're going to introduce the motion of planets or satellites, planets around stars or satellites around planets. Okay. Once again, we're going to apply all the concepts that we've developed for circular motion and then proceed from there. So let us look at a few things. So first of all, let us say that we have a star of mass, say m sub s. Okay, and we have a planet of mass m sub p that goes around the star in a circular orbit. Okay, now we'll only deal with circular orbits. I mean, in reality, the orbits are not circular; they're actually they're elliptical. But for our purposes, okay, we can start with circular motion and then just see what are the conclusions we can draw. So let us consider a circular orbit. Okay, let the radius of the orbit be some value r, and let us say that it's moving with some speed v. So what we're going to do here is we're going to connect the speed v to the radius and to other to quantities, and we'll ask what does the speed v depend on. So for an object to maintain a circular orbit around another object, okay, gravitationally, what should be the speed v with which it must travel. Now once we get the speed, we can also figure out the speed with which a satellite must orbit around the Earth to remain in a certain orbit at a certain height and all kinds of stuff. Okay, so the concept once again is very similar to what we've discussed earlier, and we can ask, we begin by saying that the object's moving in a circle, and if it's moving in a circle, we know that it must have some centripetal force, and that centripetal force points towards the center. In this case, it points towards the centripetal force on the planet is pointing towards the center of the star, and we know what that force is. Okay, we know that it is gravity between the two objects that is actually pulling the planet towards the star, and that is what is keeping the star in its circular orbit. Without that gravity, the star would simply move along the tangent. So what we have is the force of gravity, and for this we're going to use Newton's law of gravitation, which is capital G ms times mp over r square. Okay, and this is equal to nothing but m sub p v square over r. So what it says is that the force of gravity is equal to the centripetal force of the object. Great. Now we can write v. V is equal to square root of g ms over r. One of the r cancels out, the mp's cancel out, and what this does is it gives us the speed v of the planet about the star. And this speed is, as you notice, it is independent of the mass of the planet. Okay, so does not depend on mp. Now here in all this we are assuming that mp actually is much smaller compared with ms. Okay, and if that's not the case, then we have to worry about some other factor, which is the center of mass of the system and all kinds of stuff. But we'll not go there. We'll keep it simple. We'll say that the mass of the planet is much smaller compared to the mass of the star. And for instance, for the Earth Sun system, the mass of the Sun is about 2 times 10 to the 30 kgs, and the mass of the Earth is 10 to the 24. So you see that the Sun's mass is about 1,000,000 times more than the mass of the Earth. So it would really not make any difference. Okay, so what we know is that the speed v is equal to square root of g times ms over r. Now we can also relate the time period of the orbit to the radius. Okay, and in order to do this, we'll do a very simple calculation by using the basic relation that if something's moving in a circle uniformly, okay, then the speed v is equal to the circumference of the circle, which happens to be 2 pi r, divided by t, where t is the time period. So this t is the time period. Okay, so this is a very simple relation, the circumference divided by the time period. Now this is equal to square root of g ms over r. Now understand, this is a very specific case. This is for a planet star system, okay, or a satellite planet system. Now what we have is, now we can simplify this and we can square both sides, and we get 4 pi square r square over t square equals g times ms over r. and what this ends up doing is it gives us a relation between the time period and the radius. So I'm going to move the t square to the other side and rewrite this as t square times g times ms. I'm going to move the r to this side and it gives us 4 pi square r cube. Okay, and now I'm going to isolate the t, and the t square becomes equal to 4 pi square r cube divided by g times ms. And what this gives us is this is actually one of Kepler's laws, which says that the square of the time period is proportional to the cube of the radius, because you see the 4 pi, the g, m, those are all fixed, okay, once we have a particular system. And what we realize is that the time period is proportional to r cube, where it says the square of the time period, okay, for a satellite is proportional to the cube of the radius. Now this is not a simple relation to keep in mind, but make sure that you know how to derive it, and then you should be able to repeat it if you ever need it. Okay, so the square of the time period is proportional to the cube of the radius. Great. Once we have all this, we can, now we can figure out the speed with which an object must travel around a planet, a satellite must travel around a planet, and or the speed with which the Earth must travel around the Sun to maintain its orbit at a certain distance from the Sun. And those calculations are very simple. If you know the distance, you will use this equation: v equals square root g ms over r. And if you intend to put a satellite around the Earth, for instance, if you want the satellite to move at a certain time, then this expression here gives us allows us to find the distance from the center of the Earth. Mind you, this r is the radius. Okay, so this is from the center of the Earth, and if we know that distance, by knowing the radius, we can figure out the height at which it must be put in orbit. So we can figure that out also. If you know the radius, you can figure out the time period, or for a particular time period we can figure out the radius. So we can go back and forth between these expressions. Okay, that's it for this video.